Of our first speaker today. So first of all, we've got Nikola Radulov. So Nikola is a PhD student in the Arch group at the University of Liverpool, and his work focuses on integrating physics knowledge to enhance task automation within chemistry laboratories. So over to you, Nikola.
Thank you, Adam. Let me just share my slides.
Can I just add as well, if anyone has any questions, if you just drop them into the Q&A, and then we can take those at the end.
But if your slides are taking a bit. Okay. Right. Can you guys see the slides?
Perfect.
Right. Great. Thank you. So thank you for the introduction, Adam. I'm going to be talking today about how we can use physical data in order to improve task automation within chemistry laboratories. So to start with, nowadays everybody wants to do lab automation. It's meant to give scientists more freedom to work on engaging tasks. It's meant to be safer. Imagine a fully automated lab that could be running 24/7. And you could have the robots deal with any dangerous chemicals. It's meant to be faster and meant to be safer. And it's also meant to improve reproducibility through better sampling precision. Now, there's an issue. While these hold true for some of the systems out there, when you look at robots in lab automation, these are still predominantly used for sample transportation. And there's quite a big reason why that's happening. And it's that a lot of the necessary tasks require high levels of dexterity. So let's consider for a second powder weighing. First of all, it's time consuming. It requires high weighing accuracy. And it's quite tedious and repetitive. All these tasks, all these things make it really good for automation. On the other hand, you require high precision when you're handling potentially expensive materials. You don't want to deal with something that costs like £1,000 a gram and you spill it. And the task itself involves lots of different powders with different behaviors. So looking at some of the existing approaches in automating powder weighing, you've got industrial options like the Quantos dispenser that's using screw feeders to introduce flow. Alternatively, and this is the middle image here, this is from Andy Cooper's group here at University of Liverpool. They developed a dual arm system that was using fuzzy logic in order to do the task. And then you've also got reinforcement learning options with the last image. This is from Omron Corporation, and they use the single arm manipulator option. Now, what needs to be taken into consideration is that the task of powder weighing can actually be decomposed into two subphases. So first you have a powder acquisition part, so imagine scooping, and then you have powder dispensing, that's the actual dumping. And these are often treated independently, but they're actually intertwined. Oops. It's meant to be an image there, but I see it didn't render. So we've got actually two papers. One of them is looking at this end-to-end architecture. And it's essentially conditioning the acquisition phase so that the states it finds itself in before the dispensing are favorable for a reinforcement learning policy. Now, what we're going to be looking at today is only the second part, the dispensing. So, as I've said before, this can be formulated as a reinforcement learning problem, powder dispensing. For those unfamiliar with reinforcement learning, it's essentially a machine learning method where the agent, in our case, you can think of it as the robot controller, learns to solve a task by gaining experience from the environment. At each step, the agent executes an action. Here, the action is made of two movements, tool pitch adjustment and horizontal shake of the tool, and receives back an observation and reward. For us, the observation is made out of the target amount of powder, the currently dispensed amount of powder, and the current pitch of the spoon. And the reward is simply the negative absolute error between the target and the currently dispensed amount. This formulation was introduced in the work I mentioned earlier by Omron, where they had a single-arm robot manipulator to deal with the powder weighing. Now, one thing that this formulation doesn't take into consideration is the actual material properties of whatever powders you're using at that moment. So one thing is that not all materials are going to behave the same when it comes to manipulation. If you think of pouring, you can take into consideration water, and then you can take into consideration honey. One's going to be much easier than the other. And in fact, depending on the manipulation task, some materials are always going to be more challenging than the others. In powder weighing, this would be hygroscopic, deliquescent, and compressible powders, which are found to be more challenging. But then the question is, if we know that the difficulty can change depending on the material properties, we should be able to estimate how challenging a material is for the task based on these very specific properties. Now, we're quite lucky that with powders, there's actually a property that tells us exactly what we wish to know. How easy is it for a given powder to flow in the desired way? This is called flowability. So on one end, you have very flowable powders. This is the left video. You can see like it flows quite easy. Think of things like sand. They don't stick and they are easy to control. And on the other hand, on the right, you've got things like flour that tend to be highly cohesive and tend to clump. But okay, we know this property, but how can we actually use it to improve powder weighing automation? So what we proposed in a paper flip is the following pipeline. So we use the task formulation that I've just mentioned, the reinforcement learning one, but instead of feeding it randomized simulation dynamics parameters, we construct a representative set of real-life powders of various flowabilities and use those to train a reinforcement learning policy that is then zero-shot transferred to real life. So how does this look more in detail? So the first step is actually optimizing your simulation, because powder weighing tends to be quite a messy task. You would like to do this in simulation and want to do it in real life. Because of like long reset times, can be quite dangerous depending on what powders you're dealing with, but certainly messy. So you want to deal with simulation, but then there's the issue of what you're actually seeing in simulation and what you're going to see in real life. It's going to be a difference then. That's called the reality gap. So we want to minimize that. The first thing to consider is that you want to define your simulation dynamics as a probability distribution function that's parameterized over a set of parameters theta. So then you assume that if there exists a calibration task A, and this calibration task can actually give you a quantifiable measurement of the property you're trying to optimize, then all you need to do is pick the parameters of your dynamics function such that it minimizes the error between the task performed in real life and the task performed in simulation. This can be challenging in terms of finding an actual task, but for us, it's quite easy because there's tasks specifically designed for measuring flowability, like static flowability using the angle of repose method, for example. That's what we've done. So how this looks, so we have the setup in simulation, and then we had the setup in real life. And what happened was we ran the same experiment, again, static flowability measurement using the angle of repose. And we used the Bayesian optimizer in order to find suitable parameters for the simulation dynamics that would give us very close angle of repose measurements between what we've observed in real life and what we're trying to do in simulation. So here you can see the actual comparison of the powders simulated and the powders in real life, how they flow during the actual experiment. So this is on top, obviously it's a simulation, bottom is the actual experiments we've done in real life. And we've managed to get quite close to the targets. I think it was somewhere around 1 degree difference with the simulator. So, okay, you've got your data set, but then how do you actually use it to train a policy? So in order to make the learning process faster, we combined flowability with curriculum learning. Now, curriculum learning is a machine learning technique where the training data is organized in a purposeful sequence from simple to complex examples. In our case, this curriculum involved starting with highly flowable powders, which are meant to be easier and more predictable, and ending with less flowable, more cohesive ones like flour, corn flour, and so on. We compared this to broad domain randomization, where the simulation dynamics are randomly picked at every step, and the reversed curriculum, as well as just feeding this already optimized data randomly. And we found that our curriculum method outperformed all the other ones on average, both in simulation and in real life. Okay, what can we actually conclude for this? So flowability data can be used to optimize simulation parameters, and it can enable accurate modeling of diverse powders. As we've seen, we're able to get things from highly flowable, sand-like 28 AOR to more sticky-like powders. Think sodium bicarbonate would be around 43. Then you've got the ability to use flowability as a curriculum guide, which can indeed lead to faster training times and better generalizability. And finally, we showed that our method improved zero-shot sim-to-real transfer performance, and it outperformed domain randomization, which is quite commonly used for sim-to-real for sim-to-real transfer, for powder dispensing in particular. And thank you. That's